Welcome to chapter number 6, and today we want to talk about the onboard management unit, TMTC and ground stations. Let's get right into the OBMU, the onboard management unit. This is the central unit of your satellite. So all the signals from your sensors, from your actuators, from basically all control tasks need to be centralized in this single unit. And this is an example how this computer could look like, and the shape, design, and the technology depends highly on the specific mission you have. Yeah? In general, we have certain different categories we could choose. So our onboard management unit, for instance, could be comparable to an ordinary PC, to a computer. And those onboard computers, they are usually radiation tolerant, or at least radiation hard by design, because as we all know, the environment in space is not really favorable for our computer. The main advantage of those onboard computers is that they are really versatile. Yeah, they can be used for many different tasks to operate, to control, to measure, and you're not really limited to a specific function. And another advantage is that they offer a reasonable processing power as well. Yeah, that usually comes at the cost of higher mass and higher power consumption, but they are providing a reasonable processing power, and usually those space qualified onboard computers, they come with a already installed redundancy concept. One example is a watchdog, where your onboard computer produces a specific signal in certain at certain times, and it self-monitors those signals if they are coming in. Once those signals are missing, something is going on, something is faulty, possibly within the onboard computer, and one way to resolve this issue would be a reboot. Yeah? This is a watchdog. And an example would be a Leon 3 from Copham, which is a completely space-qualified onboard computer for satellites. A second group would be microcontrollers, usually commercial off-the-shelf or COTS. Those are mainly used for low-cost or CubeSat missions, yeah, where you have a small microcontroller as a central unit to manage all the actuators and sensors and the onboard software. They usually offer only a limited radiation tolerance, especially when you really go for the commercial off-the-shelf components, because let's face it, the requirements for a terrestrial application are quite different to what we have in space in terms of radiation. They are still quite versatile because we're really flexible how we're going to use it, but they offer only a significantly lower processing power compared to the onboard computers. However, usually that is not really necessary. As we said, we're mainly going to use it for low-cost and CubeSat missions, where you only require limited onboard processing power anyways. So this is not a big problem, and you save a lot of costs at that point. Redundancy concepts are quite complex for but it is possible. There are missions that have shown that they have a really good redundancy concept to operate that. And just to conclude here, a very commonly used microcontroller is some of the ARM9 family to control as an onboard management unit. The last group are some sort of different specific management units for your satellite, and the mostly used ones in this category are the field programmable gate arrays, or FPGAs, but sometimes also DSPs, so digital signal processors, or something like this might be used. The specifics of those FPGAs are that they are only used for very specific tasks that require very high computational power. So this is mainly used for payload operations. Now, where you don't have this sensor and that sensor and this could happen, that could happen. No, we only use it for a specific task. You want to process images that come in from your payload. The radiation hard design is quite complex with those FPGAs, but it is also possible, but mainly used for non-reprogrammable FPGA types. And this is the biggest disadvantage. So usually if you want to have a radiation hard design, you would choose an FPGA you can't reprogram, so you will have to put some significant effort into testing before you send it into space, because you cannot fix this problem later on. They are very, very fast, but as I said, they can only use for a specific task, so very specific, usually streaming tasks or parallel processing tasks. So this is not for everything that would be covered by the other two groups. And some example, for instance, the Vertex 3 tool, or a Spartan 6 as a more recent type for FPGAs. Let's have a look at flying laptop as an example. We have the satellite here, I've shown you earlier already. Number 11, this is the onboard computer of flying laptop. And this is a bigger picture of the onboard computer, how it looks like. But although it falls on the first category of what we just seen, onboard computers with the Leon 3 processor here, it still features an FPGA on board. So nowadays, onboard computers are not really black and white. Because you might include an FPGA for some specific tasks you want to do quite efficiently, but for the main and more broad type of tasks, you might want to go for something else that allows for this versatility. And of course, we also have to talk about the onboard software, because the onboard software would usually run on the management unit. The software can be programmed in many different languages, but mainly used these days is C, sometimes C++ these days, among some more specific programming languages for satellite operations. You basically want to use a easy to debug programming software, so you can actually also go down to the hardware layer and check if really that's going to happen what you want to happen there. And aside from managing the hardware components, of course, the onboard software and the onboard management unit is also responsible for managing your communications. And that's why we put it together in this lecture as well. Now have a look at flying laptop design. For the onboard software, it's a object-oriented approach. And we start with the hardware-dependent layer, where we have actually our hardware, our sensors, actuators, and we have the hardware drivers to connect with those units. And we have our basic operating system there, providing, for instance, the basic timing and so on. One layer above is the abstraction layer, where the operating system is basically covering all those units together. And then we go to the platform-dependent layer, where we have the device handling. So we call those hardware drivers, and its basic operating system device. We have our kernel framework, we have our data pool, where all the information from our sensors and our onboard telemetry we are recording come together. We have our communications TMTC framework. And of course, we have the framework for our FDR, our failure detection and isolation and recovery system. And above are the mission-dependent layer, where you actually apply now some functions for a satellite. Until here it's only the framework. Now we have the functions to actually work with your devices that go down to your hardware, to have your controllers for your attitude control, your temperature, and so on. You have certain report services, it's called push services in that sense here for flying laptop. And of course the FDR separated here. So far so good. Now let's talk about ground station networks and antennas. So what do we want to cover? We want to talk about the space segment and ground segment and how it is connected with each other. So how do we transfer data physically between the ground segment and the space segment? How is the data transfer organized is another question we need to ask. And how do ground station networks work? Because sometimes your satellite is not only connected to a single ground station, but to many ground stations, or even via a relay satellite that works this way. So The goal of our ground segment is in general real-time monitoring of our in-orbit spacecraft. And we want to perform uplink maneuvers, so to control the satellite, and we want to maybe even want to have range measurements, so we want to determine where our satellite is located and support our measurements of the satellite position. It could be used for ranging or Doppler shift measurements. And of course, one of the main tasks is also the failure prevention and diagnosis. So if something happens, you want to detect it early on and want to work on this if the satellite cannot do it by itself with the FDR detection. So the main functions we would support here are the satellite tracking, the telecommand signal modulation and emission, our telemetry signal reception and demodulation, so this is on ground, and the transmission and reception. But how is the data physically transferred? Well, it helps to have a look at the OC model, where we start at the physical layer and go up to the application layer. And any communication can be abstracted as those several layers. And the physical layer would usually comprise how is the data transferred physically, whereas the higher levels and layers are usually comprising how is the data transfer organized. And we have several functions across all those layers, like addressing and routing. We have the error correction, maybe even encryption. It depends on your satellite mission. But you can in general say that each layer serves the upper layer and is being served by the layer below. And we're going to talk about this in a minute, where we start with our bits on the physical layer. We go into frames on our data link. We add the frames to packets. They have a logical routing already. We go into segments for the transport, and then we go into our sessions with the data already presentation application. In general, we could split all communication links into two categories. So there is the telemetry, tracking, and telecommand as the first category, and the second category are the payload data links. As for the TMTC, the transmission of telemetry from the satellite to the ground station is presented here. Yeah, that is a downlink. But also it comprises the reception of telecommands, that is the uplink. So this is from the view of the satellite. And tracking is another function here, tracking of the satellite to determine its orbit and maybe even for the antenna control. And whereas for the payload data links, this comprises all the links that are used to download our payload data to the ground station. So usually this is the purpose why we have the satellite in space. We want to do something with the satellite. We are interested in the data. And if we have a little broader data amount, we might want to use a specific payload data link to the ground station. This could be for a geostationary satellite, a transmission of the media, like TV broadcast, radio broadcast. But it could also be a data relay between different satellites to the ground station, etc. And as I said, pretty often the systems for TTC and payload are separated. That just comes from the fact that the TTC only offers usually low data rates, but is very critical and therefore has a high reliability. Whereas the payload data link offers a high data rate, but is not so critical. And that's why you might want to split it into two separate links. How do you do that on a satellite? Well, usually, if you have your satellite, you just have, for instance, separate antennas for the separate streams coming in. That might be a specific uplink antenna and a downlink antenna, for instance. But we see many more antennas here on the surface. So that's why we have sometimes the implementation on board the satellite. In general, what we also can do is not just to receive our uplink signal, do something and send a response, but they could also straight send it back down as a relay. And that could be regenerative or transparent. Yeah? Transparent is we have a straight connection, we only change the frequency, it goes back. But regenerative would be that we actually improve the link, we reorganize it according to the OC on a different layer, reorganizing it and then send it out back again. So let's talk about frequencies. Yeah? So when we talk about frequencies, we talk about the electromagnetic spectrum. And we can have a look at the wavelength. So the more we go to the right here, the longer, the higher is our wavelength. And we go more to the left, we have the shorter wavelength. And then we can categorize those different wavelengths or frequencies by the range where they are. We start with gamma rays, X-rays, ultraviolet, infrared, microwaves, and radio links. Whereas most of the satellites will operate in the upper radio band to the microwave section. Yeah? And for instance, the flying laptop located right here with 2.2 to 2.4 gigahertz. Yeah? Just as a reminder, we have our visible spectrum, also our visible light in here. So it's a very short range here with a visible light. See here. So, which are the frequencies that are commonly used for satellites? So, according to the ITU, the International Telecommunication Union, several bands are specified. And the lowest frequency is usually the VHF, used for CubeSats and military communications between 36 and 270 megahertz. Then we go a little bit higher in the UHF, 420 to 150, also very, very commonly used by CubeSats, but also for TMTC and low data rates for payload links. Of course, still military use in that band. If you go into L band, between 1 and 2 gigahertz, this is mainly used for your GPS, Baidu, GLONASS, so all the navigational services. But also for Iridium, if you never heard of it, these are mobile phones via satellite, yeah? For mobile satellite communications. Those are also located usually in the L band. We have the S band, and the S band is the prime band for small satellites so far, and in the past also for TTNC of most of the satellite missions. However, it gets a little bit cramped these days. That's why many satellite operators actually moved already to higher frequencies. Like C-band. C-band is traditional satellite TV, especially in the US. And X-band for Earth observation, deep space missions, TTNC and military missions. So you can say in general, low-cost satellite CubeSat missions would be in the range of VHF, UHF. A little bigger micro small satellites might be in the range of S-band and could already have an X-band link for the payload data downlink. And the last two bands are the KU and KA band. And the KU band is also very traditionally used for satellite TV, also in Malaysia, and for the geostationary satellite communication. Also, because the KU band gets really packed these days, the frequency is quite limited. The bandwidth you can get within the frequency range, which led to many missions already moving on into even higher frequencies as the KA band, between 23 and 40 gigahertz, but it would usually cover the same type of satellites they operate here. But you can see this is about 6 gigahertz of bandwidth, and here we have a much broader area spectrum. But however, we always need to keep in mind that the increasing frequency goes hand in hand with an increasing of data rates. I mean, it gives us the potential to have higher data rates, but it also increases tremendously the system complexity. Yeah, so as always, nothing comes for free. But how can we put the data onto our link? And that is why we have to talk about modulation. So in general, we can say the digital signals we have, so our bits 0 and 1, are modulated onto our carrier wave. And our carrier wave is the frequency I just presented to you. Yeah, let's say it's 2.4 gigahertz, but this is just a sine wave. How do we get the data on it? And therefore, we have, in general, 3 different types. We can go for an amplitude shift key, a frequency shift key, and a phase shift key. And examples are shown here. So for the amplitude shift key, you basically reduce the amplitude if you want to have a different state than before. Let's say a high amplitude is a 1, a low amplitude is a 0, and by changing the amplitude of your frequency, you can modulate your data onto it. Problem is, amplitude shift keying is not really commonly used for satellites because you have changing conditions, and the level of the signal might change due to other effects. And that's why it's a little bit too prone to failures and issues, and that's why you might want to look into frequency shift key and phase shift key. Yeah? So frequency shift keying, you basically have 2 sets of frequencies, roughly the same range, and you just switch from one frequency to another, let's say higher frequency, and this is how you show or modulate your data between 0 and 1. And for the phase shift key, you use the same frequency, but you apply a phase shift. And if you detect this phase shift, you also have a change in your data. And this PSK, phase shift key, is preferred in satellite communications. Very easy to explain is a binary shift keying where each transmitted symbol has 2 different states or 2 different phases. And those represent the bit 1 and 0. If you go higher, like a quadrature, PSK, QPSK, each transmitted symbol has 4 states. So now we have 4 different phases. Yeah, let's say 0, 45, 90, and 270. 90, and that's not correct. 0, 90, 180, and 270 degrees as a phase shift. And each of these phase represents now 2 bits. Yeah? So we have 4 sectors, and we choose which sector belongs to which sequence of bits. And that's why we have to be a little bit careful to understand the difference between the bit rate and the symbol rate. Yeah? Although we have just 1 symbol, it actually represents 2 bits. So with the QPSK, our symbol rate is fixed, but the bit rate is actually twice the symbol rate. Another important thing we need to understand are the antennas. So antennas are used to receive and transmit the electromagnetic waves. And they have the same characteristics basically in both directions. So they can receive and can transmit. The characteristics are pretty much the same. The most important characteristics of an antenna is the antenna gain. So the gain describes the directivity of the antenna. So, for example, which proportion of the power is transmitted in which direction. If we have an antenna that's more focused, we have a higher signal level within the focus, but if we go out of the focus, we have a lower signal there. And this is how we achieve a higher gain into a certain direction, directivity. A high gain antenna for transmit or receive, a lot of power from one direction. Yeah? So this is what we said. A high gain antenna has a really narrow focus. This is how we do that. And the gain is given as the ratio of the gain to an ideal antenna. And the common unit used is dpi, related to an isotropic antenna. So an antenna that transmits in all directions isotropically. In general, we can say the higher the gain, the smaller is the bandwidth. And as an example, for a ground station for small satellites, like in the IRS, the antenna has a beam width. So this is the angle, how narrow our antenna opening angle is about 3 degrees. And that means our ground station antenna has to point very accurate to the satellite within those 3 degrees. Otherwise, if we mispoint, we have a lower signal, we might not be able to receive our signals from the satellite. So what are commonly used types for antennas? So one is here, this is a turnstile antenna. So all the 3 antennas we see here work in S-band, around 2 to 2.4 gigahertz. Turnstile antenna for onboard of the satellite. So it has a very broad opening angle. So definitely more than 90 degrees in one direction, about around 180 degrees almost. So this opens up one half sphere. And this is commonly used if we want to have a quasi-isotropic antenna for our satellite, for TTC. So we want to receive the signal from the satellite regardless of the orientation of the satellite. If we put 2 of those antennas on different sides of the satellite, we should cover all the sphere around the satellite and should be able to establish a link with the satellite regardless of its pointing. So this is commonly used for TTC. However, the gain is not too high because we cover a lot of range. Next type is a medium gain antenna. This is a horn antenna used for payload links. So you have an opening angle of around 10 to 20 degrees, and you have some significant wins in gain. And the last category are like high gain antennas, as a 2.5 parabolic antenna used for ground stations that can achieve another very high gain compared to the other 2 types. But as I said, the beam is quite narrow. Why is it all important to have different types of antennas? So if we have a look at this, we have our transmit radio on board, let's say, our satellite, and this radio, our transmitter, is connected via some cables to the antenna. And we have a certain transmit power, then comes the cable. When we lose some of the power, is attenuated in the cable, and then we have our antenna with the antenna gain, and we get to our EIRP, our equivalent isotropic radiated power. And then we have our path. So this is the distance we need to cover. And of course, now we have a lot of path loss depending on the distance to our receiver. Then we have our ground station antenna here, and we have our antenna gain, which is again connected via a cable with some attenuation, and then we get to our receiver, our RX radio, and with a certain power level. And this power level needs to be above a certain threshold for our RX sensitivity, so we are able to decode, demodulate, and actually to have our signal there without too many transmission errors. And depending on the margin, we can actually distinguish the quality of our link. There are certain factors that might affect this whole communication link between the transmitter and the receiver. We said we have our cable, so we have attenuation between the transmitter and our antenna already. We have cables, equipment, and other introduced noise. So that's why this attenuation, this is where it comes from. But also our antenna has some losses due to polarization, mispointing, or thermal noise. Yeah? Then we have our path, and there might be rain, for instance, so we have atmospheric disturbances, again on top of the free space loss we just saw there. And basically the same that applies to the satellite antenna also applies to the ground station antenna. When we have polarization loss, we can have a mispointing of the ground station, but also thermal noise. So ideally, we are watching into cold space, so it should be a relatively low level of thermal noise there. However, we have the introduction of some ground-related noise in the surrounding of our ground station, and there might be even more thermal noise if we point our antenna, for instance, in the direction of the sun, which is quite warm, so it introduces additional noise. And an external factor could also be interferences by external factors like here transmission tower or different satellites that introduce different interfering signals. And the only way to deal with this, if you can, is by installing filters to filter out those unwanted interferences. But if it's an interference on the same frequency as yours, then there's not much you can do. And that's why the ITU is there to help you coordinate the different frequencies used by different players in the market. This is just one link to one slide to explain the free space loss a little bit better. As we said, the free space loss is due to the distance of the distance d. The signal needs to travel between a sender and a receiver through air or through space. And the only thing this free space loss depends on is the frequency and the distance. So it's independent of your atmospheric environment. And the loss rises quadratically with the distance. So this is very important to keep in mind. Yeah? So if you go twice as far with the satellite, your path loss is actually 4 times as high at this point. So, and this is an example for S-band. If you go from a 600 kilometers low Earth orbit, you have a free space loss in S-band of around 156 dBs. But if you go with the satellite now to 36,000 kilometers, so to GEO, you have a free space loss at the same frequency of 191 dBs. So this is already 35 dBs more by the distance. And keep in mind, I mean, 35 dBs, then is even more of the difference between the high gain antenna and the low gain antenna. So even here, we only have 30 dBs more if we go for a small antenna to a really highly directed antenna. So that's why we have to keep in mind always the free space loss when we do that. And even if we go now into a higher frequency, but stay at the GEO, we also see that the free space loss increases. This is how it can be calculated. So if you want to prove that and to check on it, please go ahead. This is the formula to calculate the free space loss. And now let's talk about the ground segment in general. So we had our antenna and our satellite somehow. The antenna is connected to all sort of, we call it HF stuff. So all the radio frequency components, like amplifiers for the reception or for the transmission. We have duplexers, diplexers to feed our systems together into one line. We have converters for the frequency, and we go maybe to a intermediate frequency. But we also have to consider all the other components we have to have for the antenna, because the antenna, as we said, needs to point towards the satellite. It also means that it needs to be able to point to the satellite, and that's why we have motors to steer the antenna and to follow the satellite, and an antenna control unit, and eventually even a tracking receiver. So you use the same signals coming from the satellite or specific satellite signals just for the tracking. You have a specific reception path for this via a low noise amplifier, an L converter into a tracking receiver to get a signal if you are pointing at the satellite or not. If you're not pointing at the satellite, the antenna needs to steer. If you're pointing at the satellite, easy spoken, you don't need to steer the antenna, and this is the task of the antenna control unit ACU. Let's have a more specific look at different parts of a commonly of an example ground station for small satellites. We start with our high power amplifier here. So let's better start with our RF unit, our modem, our modulator and demodulator. So let's say you have a telecommand. You introduce your telecommand into your TMTC front end, so you can do the checkout. The TMTC front end will do maybe the forward error correction, the encoding. Then you do the modulation of the data, and you convert it to the frequency where you need it. And this is the output of this unit here is already the signal you want to have at the satellite. But since you have to account for the free space loss and all the other disturbances, you have to increase the power level, and that's why I use the high power amplifier here. So now you tremendously increase the output power. You have a filter to transmit only the signal you want to transmit, and then you feed it via a deplexer into your antenna. Incoming signals will basically follow this path backwards, but the diplexer has the task to split it into this range is basically just a filter, a bandpass filter depending on the frequency. And since our receiving signal will come on a different frequency, it's easy to put it into the reception path where we have a low noise amplifier, a filter, and then the down converter section to go down from S-band into our intermediate frequency range, intermediate frequency of usually around 70 megahertz. The signal is then demodulated and going by the TMTC front end to our basic bits of the signals we want to have. And at that point, that's more from the real life application, where we talk about TX, so transmit and receive locks. So what is a lock? The receivers have to listen at the right frequency to receive the signal. Now, yeah, you keep your ears open. You want to hear the signal if you're the receiver, but the frequency of your signal is actually coming in differs because of the Doppler shift. Yeah? The satellite is passing over a ground station at a high velocity, and it's approaching you, and then it's flying away from you. So the Doppler shift has a big influence on your receiving, on your frequency. And that's why you have an internal control loop that locks on the received signal. This is the so-called carrier lock. So it constantly searches for your frequency within a certain range. I mean, you know how big the influence of the Doppler shift will be, so you know the range where you need to look for the signal, and you do that. And once you have found the maximum of your signal, this is a carrier lock. And this is usually done automatically by the ground receivers. For the satellite receivers, you do a sweep at the beginning of each pass. Yeah? So your uplink signal frequency is changed constantly over the complete range due to the possible Doppler shift. So whenever you want to establish an uplink with a satellite, you switch on your signal, but the satellite doesn't know where to find the signal now. Yeah? To lock on this, that's why you sweep, you shift your uplink signal within the Doppler shift range until the satellite has found it, locks onto it, and follows this. And the satellite will also tell you when it has acquired the so-called carrier lock. And that's why you usually have to sweep at the beginning of each satellite pass. But the receivers, they also have to interpret the symbols they receive at the correct speed. So this is now the log onto the data rate, or the symbol rate. So as we said, our signal is not just a frequency, it's also our modulated data. So if you want to get the modulated data, we need to know what is our data rate. So how often do we have the frequency shift, for instance? And that's why you have a certain sequence where you have a lot of those shifts, and you try to detect the begin and the end of the shift, so you know how long is the duration for each bit. And this is the so-called bit lock, which we see here. You have obviously 4 states here, so it's a QPSK. So at this point, we also have acquired a bit lock, and we can now interpret the single bits. But how do we assess the link quality? And this is done by the so-called link budget. And this is one of the early stage things and analysis you do when you have a satellite mission. You need to do that. You need to find a way to estimate your later on satellite link, and if all the components you have on board your satellite will be sufficient to establish a link between your ground station and your satellite and vice versa. So, as I said, the link budget calculates the quality of the transmission. And the goal is to maintain the energy per bit to the noise power spectral density ratio, or the EBN0. And you want to have this above a required limit or margin. In other words, this is exactly what is described by this. So you have your link, you have all your different components you can choose now, but at the end of the day, it's important that your signal power of your received signal is above the sensitivity margin, sensitivity at a certain margin, and this margin is the margin for your link budget, and the link budget is used to determine this margin. Yeah, a low margin will increase the bit error rate up to an unacceptable level. So you usually will have a low bit error rate anyways because of those disturbances on the link, but at one point it increases above a certain threshold that it's unacceptable for you to interpret your link. And your EBN0, your energy per bit to noise power spectral ratio, spectral density ratio, can be calculated by this formula, where you basically have, you account for all the losses you have on the path, the gains, and the system noise temperature. And of course, your effective data rate is also a factor, and then you can calculate your bit energy. The signal level or the power must be calculated in every case to the link to make sure that the receiver sensitivity is sufficient. Yeah? As we said, there's a reason why we use different antennas for our TMTC and our payload link. And this is exactly because of the link budget. The link budget outcome is that you actually choose different antennas, because if you have a high gain antenna, yes, you have a very sufficient link margin in nominal cases, but what if your satellite is for some reasons pointing inverted 180 degrees, so in the different directions? In different direction, you don't have any signal then if you have a high gain antenna on ground. Even worse, as we said, one of the main goals and the main requirements onto our communication system is to be able to determine what is going on with the satellite in those cases. And we cannot if we don't have a signal. So that's why we chose, according to for those contingency cases, a different antenna, so to be able to still establish the link under those conditions. And the important parameters to analyze this link are the transmitter EIRP, the equivalent isotopic radiated power, which is a measure for the signal power transmitted taking into account all losses and the antenna gain. So this is the basic outcome of the output of your transmitter at the very end to the interface to the air or the space. And on the receiver side, we have the GOT, the gain to noise temperature, as a measure for the quality of the receiver. And here are just some examples where you can see the different EIRPs for the satellite and for the ground station. So the satellite transmit EIRP is around 3.3 dB watts, whereas the ground station EIRP is up to 43 dB watts. So you can see it's much higher on the ground, of course, because you have, compared to space, you have unlimited resources. You can have a very high amplification on ground and very high gain at the cost of a lot of power consumption. It doesn't matter on ground, at least not as much as for the satellite, where it goes really into cost. How can you improve the link budget? Well, of course, you can always reduce the bandwidth, respectively the data rate. You can change the frequency, because when you go for a lower frequency, you have less influence of the path losses. Or change the frequency because the atmosphere might be more transmissible for this certain frequency. You can reduce the distance between the transmitter and the receiver And of course, you can always improve the quality of your equipment. You can improve the antenna pointing, so you have a better direct connection. You could use also larger antennas if you already have a good antenna pointing, and you can add more amplifier power. In case you have some interfering signals, you also could try to get rid of those. And as a last resort, you can always wait for better weather if that's the case for increase. Yeah? We had atmospheric influences, bad weather, heavy rain might be a reason here. However, as you can see, in terms of satellites, most of the options are not really practical. Yeah? We have a satellite that has a certain equipment, that has a certain orbit. We cannot change the distance and we cannot change the frequency. What do? Well, an easy way here, or a solution, is to introduce the forward error correction by FEC, which are codes to reduce the necessary EBN0 for the same bit error rate. And this so-called coding gain is, of course, costing you some data rate. So the effective data rate is lower than before, but you are less prone to influences, external influences. And you can see here the uncoded, this is the bit error rate over the EBN0. And if we introduce, let's say, a Reed-Salomon coding, at the same point, let's say we want to have a bit error rate of -3. So we are at this point, and we have EBN0 of around 7. If we introduce the Reed-Salomon coding for the same bit error rate, we only need 6.5, even a little bit less of dBs as a margin. So our margin is already significantly lower for the same bit error rate. Or if we have a established margin of, let's say, 7 dBs, and now we introduce a coding, we can check our, it doesn't even go that far, so we should go to maybe, let's say, 5 or 6. We're here at 6, it's almost a point, but you get the point. You need less margin with the coding gain involved. So if you have the same link margin with a coded and uncoded link, the coded link will give you a higher link quality and a lower bit error rate at this point. So now let's finally have a look, after we went into the physical layer, how the data transfer is organized. So now we go from frames, packets to segments. So the basic concept comprises how the actual data to be transmitted is put into packets, frames, or data units on different levels. And those fields typically have a header, a footer, and a data field. And the following measures can be taken for a stable link communication. You can add checksums. You introduce checksums onto your data to dismiss corrupted data units. So an example are the cyclic redundancy check, the CRCs. So if you detect that the checksum is wrong, you know some of your data is corrupted within the link, so you dismiss the data at this point. You can have synchronization markers, which are used to enable the receiver to detect the beginning of a new data unit. This goes into the bit log. Yeah, with the synchronization markers, you have a synchronization sequence, and within that you have the bit log. This is introduced within this field. And we can use data randomization to allow a constant bit synchronization. Because imagine we have a very long sequence which is all zeros, and then a very long sequence that is all ones. That can cause problems because at one point you cannot redetect the edge, the change between the 0 and the 1 we set for the bit log, right? So we might lose the bit log at this point because the receiver is just not sure why it's not detecting any changes after a long time. That's why you can randomize your data, pseudo-randomize your data to introduce a more common swap between the different phases. and to allow for better synchronization. And lastly, the data is encoded with a forward error correction and decoded, including the error correction upon reception. But how is this in general done? I mean, those are all different measures we can take to improve our link. But at the end of the day, we have a satellite and we have a ground station. And if you not only want to communicate with your single ground station, but also with others, you need something which is called standardization. Because you need to have a common standard that most of the ground stations fulfill to be able to talk with many different players. And one way for the standardization is the CCSDS, the Consultative Committee for Space Data Systems. And the lower layers are the physical coding and protocols are defined by the CCSDS. See examples. And there is also the ECSS, the European Corporation for Space Standardization, for higher levels, higher layers, and the protocols. So this is one way to follow the standardization, at least in the European. This one only in the European market, but the CCSDS is also a worldwide standard and commonly used by ground stations and satellites. And yeah, this is one example for the uplink, how it's organized. We have our data in so-called CLTUs, the Command Link Transmission Unit, with different headers and footers. We have our data in there. We have some code blocks introduction, and we have between the CLTU, we have the transfer frame. With a frame header, our TC frame data, and our TC error control. And then we have several fields in our frame header and also in our TC segments. And finally, we go to packets, and each TC source packet is again equipped with a header and our data field. And finally, here we have our data included in the command data. So this is how we go down to the data level from the CLTUs. And for the downlink, we have the so-called CADUs. And one CADU has the synchronization marker and the Reed-Salomon code block. You have your data inside of your Reed-Salomon code block and your Reed-Salomon check symbols at the end to do some error correction. We have some redundancy bits here. The TM transfer frame has another frame header, a frame data field, and a frame trailer. And the frame header has several units like the spacecraft ID, for several other points, counters, and so on, for checking on the signals. Spacecraft ID, very important to check that you actually communicate with your satellite. So that's why you have a unique spacecraft ID. And the frame trailer has also some other flags that can be used or might not be used in your case. And if you go down to the frame data field, you have the TM source packet that has another packet header with a packet counter, a data field header, and your telemetry data at the end with the CRC, so with your cyclic redundant check symbols. So this is an example for the CCSDS communication. And now let's talk about ground station networks. So all what we are talking about until now was about how is the satellite data acquisition organized, and how do we get the data from space to ground or from ground to space. But we were only looking into one ground station. And with the standardization, we already introduced the concept that we might not only have a single ground station, but we might have more than one ground station that is compatible with our satellite. And I want to bring an example with the Flying Laptop satellite at this point. So the main antenna for the Flying Laptop mission is its own specific ground station in Stuttgart, the 2.5 meter commercial S-band and ham radio S-band downlink antenna. This one. Of course, the systems are upgraded right now with another 4.5 meter SX-band antenna in the background, you've seen there, and a high precision E-band ground station for satellite tracking function. But this is not really important for our for Flying Laptop. This is just the antennas that are installed in Stuttgart. For the Flying Laptop, the ground station network, besides its own ground station, has ground stations by the DLR, the German Space Operations Center in Weilheim. You can see it here. So this is the site in Weilheim where we have 30-meter antennas, we have 15-meter antennas, and I think a 7-meter antenna as well, all in S-band. You have the, we use the GFZ in Svalbard, Mjolnesund. This is this station here. It's 2 different antennas next to each other for S-band communications, 3.7 and 4 meter in diameter. And I forgot to mention the DLR GSOC is also giving access to its ground station network, which is worldwide. And one example is here the O'Higgins station in Antarctica. And also we use for the ground station network Flying Laptop the UPM antenna right in Serang for S-band reception, and the antennas by the Malaysian Space Agency on my side, Banting. Flying Laptop also uses several optical ground stations and is now being upgraded to a multi-mission operation. But let's have a look at this, how our ground stations are located all over the world. As we said, we have the Stuttgart 2.5 meter station here, and the Weilheim 50 meter antenna, and also the Oberpfaffenhofen optical antenna link. Now, those are all in Central Europe located. We have the GFZ antenna we saw in Svalbard. Those are the 4 meter antennas here. We have the O'Higgins antenna we saw in Antarctica, and we have Inuvik here, another 15 meter or 30 meter antenna in the north of Canada for S-band communications. And in terms of S-band, we also have the UPM antenna here and the MISA antennas in Malaysia as an option. And all on top is just also the optical ground station by the European Space Agency on Tenerife, right located here. So this is a already rather comprehensive ground station network for a small satellite mission. Now, let's have a final look at the satellite control center. And the requirement and the objective of the satellite control center is to control our satellite. Yeah, this is where all the selected commands come together based on the defined mission. Also, the binary profile is constituted there and is time tagged. So you have specific times where you comprise your signals together, your data, before you transmit it to the satellite. The transmission of the TC frames is happening there, and also the checking of the software and the hardware status of your satellite. Yeah. And as we earlier said, also Watchdog is involved here to check the boot up status, for instance, of the satellite. And most importantly, the failure check is happening there. So your control center controls the satellite, so is putting all the signals together, all the commands together to control the satellite, is checking for failures, and is receiving the data that is coming back from the satellite. And instead of me explaining now how the center is built up, it's installed, what are the components, my colleague Steffen Geiser from the IRS in Stuttgart will demonstrate you now the ground station of Flying Laptop doing an active pass, and the video, you can now proceed to the video, which is around 22 minutes. And if there are any more questions, please don't hesitate to ask me. That's it from my point, and thank you very much for your